talk, and it's a complete disaster at the moment. I'm tempted to cram way too much material into way too little time, and I also need to draw many, many pictures, which might make sense in real time, but from experience, I can tell make no sense when they go up at the speed of light in a computer talk. So, the real purpose of my talk is to explain what the title means. And I should say this is work in progress with Jaroslav Trinka and a mathematician at the University of Montreal. Just as a personal comment, this mathematician at the University of Montreal is someone that I've known since he was in grade 9 and I was in grade 10. And it just so happens that all these years later, he's precisely one of 3 mathematicians in the world who's exactly the expert in the subject that we desperately needed an expert in. So his name is Hugh Thomas, is absolutely brilliant, wonderful guy. Just a few general words before getting into the talk and explaining what the title means. I'm, of course, here at a meeting of brilliant people who study integrability. The reason I'm here is that much less brilliant people have been drawn into the subject following their nodes and thinking about very basic physical questions, ultimately originally motivated by trying to make predictions for collider physics experiments like the superconducting supercollider historically and the LHC of calculating scattering amplitudes in gauge theories. Of course, most of the progress has been, really dramatic progress has been in planar n equals 4 super Yang-Mills, and I just remind you this theory is the same as the real world at tree level. Okay? At least real glue at tree level, so it's a toy model, but as toy models go, it's closer to the real world than many, many other toy models that we've talked about in theoretical physics over the last 30 years. So that's the physics. On the one hand, this physics has been connected to string theory and integrability in ways that are famous and well known to many of you. This theory is integrable. There's an infinite dimensional Yangian symmetry associated with it. But on the other hand, in the last really 10 years or so, but more and more as time has gone on, we've been seeing connections between this physics and some quite remarkable and novel new structures in mathematics. So on the math side, there are structures in number theory, in combinatorics, and the subject of most of this talk, which is also the one that seems to be most closely connected with the Yangian symmetry, are new structures in what you can call positive projective geometry. So there's a notion of the positive Grassmannian. That was something that was studied and understood around 3.5, 4 years ago. In a very concrete sense, the positive Grassmannian is extremely closely connected to the Yangian. In some sense, the structure the structure of the positive Grassmannian can be thought of as a generating function for all free Yangian invariants of the SL4/4, or more generally the SLM/M symmetries. And more recently, there was a further generalization of the positive geometry. The positive Grassmannian is something that very fortuitously for us, mathematicians had run into themselves for completely independent reasons in the mid-2000s. But we could think of them as giving us a novel set of building blocks for building scattering amplitudes, the building blocks that made the Yangian symmetry manifest. But there's a separate question of why the building blocks were put together in the way that they needed to be put together to build an amplitude. And that needs a further extension of this idea, the ideas of the amplituhedron, which have been developed over the past couple of years, and something that we're continuing to look for, which is a dual to the amplituhedron. A dual in the sense of Desargues from 1500 of exchanging points and planes, the most ancient duality we've ever seen. What we're looking for is a generalization of that standard duality in projective geometry uplifted to this amplitahedron context. I won't have time to really talk about this today, but this has been a big focus of our work over the past couple of years. And what I'm talking about today is really largely motivated by trying to discover what this dual amplitahedron is, even though I'll say very little about it. Okay, so that's why, anyway, that's why I'm here with fancy people like you, is that it seems like these interesting structures in mathematics are very closely tied to these deep integrable structures that have shown up in planar n equals 4 superunions, and we'd like to understand both physically and mathematically better what is going on. So what I'm going to talk about today is as far as we can tell, what the most primitive and fundamental definition of the amplitahedron is, which is quite far away from the definition that we gave back in 2013. As far as we can tell, all the extraneous parts of the construction are gone. It seems to be, I can't imagine it could get more primitive than this. If it does, I'll give another talk and apologize for lying. But there are two ingredients to this. And one of them is that, and that's the content of the title, so on the one hand, we've now understood that scattering amplitudes, we normally think of scattering amplitudes as functions. They're functions of kinematical external data. And if we talk about what we can think of as the integrand of the scattering amplitude at loop level, then there are functions of the loop momentum variables. And that's the object that I'm talking about. Now, in the context of the story of the amplitahedron, we've already gotten used to thinking about a very close cousin of the scattering amplitude as a certain differential form. A differential form that doesn't live in the usual space of momenta and external data, but acts on the space where the amplitahedron lives. However, part of the story of stripping away all the extraneous ingredients is the realization that the scattering amplitude is actually directly a differential form on the space of the physical kinematical data. Okay, so that's the first point. It's not a function, it's really, truly a differential form, and it's, of course, crucially associated with supersymmetry, the fact that this is true. So the scattering amplitude is really a differential form on the one hand, and on the other hand, its dynamical content is fully specified in a very concrete notion of a binary code. As we'll see, what completely specifies what the amplitude is in the end of the day is going to involve looking at a certain geometry associated with the external data, looking at the certain geometry associated with the external data, projecting in certain directions, and looking for patterns of plus signs and minus signs. Okay, so it's all going to boil down to binary bit patterns and matching pre-specified binary bit patterns. And in a very concrete sense, if someone handed you the amplitude, it's a binary code. You would look at it in these particular directions and confirm that, yes, indeed, it has the correct sign flip patterns that are needed in order for it to satisfy ultimately all the physical properties of the amplitude, the fact that it factorizes, locality and unitarity, all of those things are a consequence of this binary code structure. So those are the two things that I want to at least give some flavor of in the lecture today. Okay, is there an eraser? Oh, here's an eraser. Okay. So just so we talk about some concrete things, let me remind you of the usual way of talking about amplitudes in this theory. The usual way is that it's a function. And in order to bring out especially the dual superconformal symmetry as nicely as possible, we think of the amplitude or the integrand at loop level as a function of some four-dimensional vectors ZA. These are almost the momenta of the external particles, but not quite. They're a little, they're simply related to the momenta, but the dual conformal symmetry acts nicely on these guys. These are the so-called momentum twister variables. Shouldn't surprise you that twisters are useful because we're trying to make conformal symmetry as manifest as we can. In this case, it's the dual conformal symmetry. So these are the momentum twister variables. There are super momentum twistor variables. So they're the super partners of these guys. I don't know what index to give them, some super index, I. Okay, and at loop level, we should have a function of a number of loop momenta. The loop momenta in this picture, the z's are 4-dimensional vectors up to rescaling. So they live in a 3-dimensional projective space. And the loop momentum variables just simply turn out to be lines in this 3-dimensional projective space. This is part of the standard twistor correspondence, that points in space-time are related to lines in the corresponding twistor space. And we denote these loop variables as a line. So we imagine, so these things live in some 3-dimensional projective space P3. And these things are lines in the 3-dimensional projective space that we can specify by giving 2 points on them. Okay? So on an A and a B for loop 1 up to AB for loop L. Okay, so that's what amplitudes normally are, or the integrand. Now, a standard part of the amplituhedron story, before I tell you what the amplituhedron is, I'll tell you the space in which it lives. And the first important thing is that supersymmetry, there's no super geometry here. There are no super variables. Everything immediately becomes bosonized. Okay? So we have an interesting bosonization of supersymmetry. And part of the point is that the external data, the information, so normally this is labeled by n and some variable k, and n external particles, and k. K is the degree of this object expanded in powers of eta, which are Grassmann variables. So this thing would have weight 4k, or have 4k etas in it. But in the amplituhedron space, before even telling what the amplituhedron is, the external data is extended to be much higher dimensional. So instead of being 4-dimensional, it's 4 plus k dimensional. So the ordinary bosonic momentum twistors live in the upper 4 components of a vector. We have k extra components, which is where all the super information goes, but there's nothing super yet. So I'll just call them some extra bosonic parameters zeta. And the 4 can be uniformly replaced by any even m throughout this talk. So in fact, the general geometry is best defined and should be thought of for all possible values of m, as we'll see a little bit later. Okay, so we have a k plus m dimensional thing. So this is already some extraneous extra stuff that we apparently have that's not there in the super amplitude. On top of that, in this k plus m dimensional space, so in this big k plus m dimensional space, we have these points, these z's, but we also have a k-plane. So we have a k-plane y in k plus m dimensions. And in fact, it's that k-plane that invariantly tells me how to distinguish the bottom from the top components. So geometrically, you imagine that you have a k-plane. So we have and what I hope is self-explanatory notation, we have a k plus m dimensional space here, and we have k of the directions that are picked out by y. So this is a k-plane in the k plus m dimensions. Z is, well, some generic vector in the k plus m dimensional space, but there's the piece of z that's orthogonal to y. Those are the ordinary bosonic momentum twistors, and there's the piece that's inside y. Those are the x's. Okay? So with the data of this, these points in k plus m dimensions and a k-plane in k plus m dimensions, I can at least pick out what I mean by the little z's. Okay, so all right. So how do we finish the story? So again, this is in the standard picture of the amplituhedron. We think about a certain differential form where all of these z's are thought of as being constant fixed external data. Sorry, and I forgot to say, this is the case. This is all we have when we're talking about tree amplitudes. We just have one k-plane. The information about loops in this geometry is included in the following very simple way. Let me collapse the picture of the k-plane to just being a line. So here's the k-plane. And we imagine, for example, at one loop that there's actually a k+2 plane as well. We can call the k+2 plane YAB. So that's a k+2 plane that contains the k-plane Y. Okay, so this is the k+2 plane. And if we have two loops, well, we have some other k+2 plane. So this would be some YCD. Okay, this is a k+2 plane. This is a k-plane. And they all intersect on one common k-plane Y. Okay, so that's the space in which the amplituhedron lives. It's a space of a whole bunch of k+2 planes in k plus m dimensions, and those k+2 planes overlap on a common k-plane. In this big space, we have a certain differential form. Let me restrict to just talking about trees so I don't use time for notation. So we have a certain differential form. It's a m times k form. So the dimensionality of the space of k-planes, the Grassmannian, the space of k-planes in n dimensions is k times n minus k. So the dimensionality of the space of k-planes in k plus m dimensions is m times k. So we are looking for an m times k form which depends on this y, and the external data are fixed. So we have to give this differential form. We look for some differential form in y space. And from this differential form, there's a canonical way of extracting the superamplitude. I'll give an example in a moment, but I just want to say there is a differential form in town, and I'll tell you what specifies the differential form in a second, but that's the object that we have been playing with for the past 3 years until this new picture came along, is that there is a differential form on the amplituhedron space, on the space of y's, and there's a very simple way of extracting the superamplitude from it, but it's not directly the superamplitude itself. Okay, so now let me at least tell you what the logic is. So this is the space in which the amplituhedron lives. I haven't told you what the amplituhedron is and how it's related and how it determines the form. So this is the dictionary that's going to convert geometry into physics. So first of all, in this space, again, restricting to a trees, let's say just restricting to a trees for a second, in the space of k-planes in k plus m dimensions, in this space, there's going to be a certain region. I'll define what the region is in a second, but once you give me the external data associated with the external data, so once you give me these z's, there's going to be some shape in the space of k-planes in k plus m dimensions. So that shape is the amplituhedron. So that's the geometry. And what turns it into physics is that we have to find a certain differential form. We have to find a differential form omega as a function of y. Again, it depends on the z's. And the purpose of this differential form, and what fixes this differential form, is that this form has singularities. In fact, logarithmic singularities, which I'll specify what it means in a second, logarithmic singularities on all the boundaries and only the boundaries of the amplituhedron. So there's a geometry, we specify the external data. There's a geometry in GKK plus M, and associated with that geometry is a specific form. The form is a slave to the geometry, but it's a richer object because it depends on y, it depends on the external data, but it's fixed by having this particular kind of singularities on the boundary of the amplituhedron. Now, what do I mean by logarithmic singularities? Well, let me give the very simplest example of an amplituhedron, and in fact, what the amplituhedron is. So I'll just give a a cartoon of the logic that leads to this object. It's an incredibly simple geometric object. There's no reason that mathematicians couldn't have run into it and discovered it 100 years ago. In fact, they probably would have if various accidents in Göttingen and in the Italian School of Algebraic Geometry didn't happen. They probably would have been discovered 100 years ago. Because all it is a generalization of the notion of a triangle. So the logic is the following. We imagine thinking about a triangle. We can generalize a triangle to a tetrahedron or a simplex. And lifting this notion from plane geometry or projective geometry into the space of projective geometry can be thought of the space of lines passing through an origin in n dimensions. If we lift this to generalize it to something that makes sense in the space of k-planes passing through an origin, then we get the positive Grassmannian. So on the one hand, triangles and simplices, which are the building blocks out of which you can build all kinds of more interesting higher dimensional objects, the building blocks themselves get lifted and generalized into the positive Grassmannian. But there's another natural generalization of triangle into the inside of a polygon. And that generalizes into the Grassmannian, exactly the analog of the triangle, turns into the amplitahedron. The triamplitahedron. And then there's one more step, which is to learn how to hide particles. And hiding particles from this geometry takes you from the triamplitahedron to the amplitahedron at all loop order. Okay, so that's just a rough logic, but just to keep in mind, all we're doing is generalizing the notion of the inside of a triangle or the inside of a convex polygon into the Grassmannian. And so I can already tell you what this form is in this very simple case where we're actually just talking about a triangle. So let's say you imagine that we have a two-dimensional space, we just have a triangle, and I have some y, and I want to write down a differential form in this two-dimensional space that only has singularities. It has logarithmic singularities. Log singularities means that locally, in the neighborhood of any singularity, locally, there's a choice of coordinates where it looks like dx1 over x1 up to dxd over xd. Okay, so that's what it means to have logarithmic singularities. It's the simplest, most canonical singularities a differential form can have that just generalizes the usual dz over z pole when you have a singularity as a function of one complex variable. Okay, so a form has logarithmic singularities if in the neighborhood of everywhere where it has singularities there's some choice of coordinates where it looks like just a bunch of d logs. Okay? Each one of those is d log x1 up to d log xd. So how do I write down a form that has logarithmic singularities only on the boundaries of this triangle? Well, a very simple way of doing it would be to represent all these points as, for example, z1 plus alpha z2 plus beta z3. This is, I'm imagining all these, everything is done projectively. These are all three-dimensional vectors up to rescaling, so that allows me to write it in this particularly simple way. And so the form which has logarithmic singularities on the boundaries of the triangle is then obviously just d alpha over alpha, d beta over beta, okay? Because it's alpha and beta going to 0 and to infinity that correspond to hitting all the boundaries of the triangle. And I can write this in a more invariant way as y dy dy, and they're contracted with an epsilon symbol. Every time you'll see a bracket in the rest of this talk, it means contracting with an epsilon symbol. And then there's if the corners are z1, z2, z3, you would write a z1, z2, z3 squared over yz1, z2, yz2, z3, yz3, z1. And so these poles indeed tell you that, that you have singularities when y lies on the line 1, 2, 2, 3, and 3, 1. But on top of that, there's more. Because on top of that, if you take the residue around that pole, now that you're localized on this line, the further singularities only occur at the corners 1 and 2 and not anywhere else. Okay? So this is a very simple example of a geometry, a triangle, and a form with logarithmic singularities. This guy, which is tied to the triangle. okay? And is determined by putting logarithmic singularities on the boundaries of the triangle. What determines scattering amplitudes is just generalizing the triangle, okay? And when we generalize it in this direction, we have all the Yangian invariant building blocks associated with the positive Grassmannian out of which we can build the amplitude. But we don't know why we're supposed to put all the triangles together in the way we're supposed to in order to get the answer. But this picture tells us ab initio what the question is to which the amplitudes are the answer. We generalize the polygon into the Grassmannian. And we once again ask for a form with logarithmic singularities on the boundary of this guy. There's a unique such form. And the properties of the geometry dictate the physical properties of the form. For example, the singularities of the form, the singularities of the amplitude, correspond to the situations where y hits the boundaries of the amplituhedron. And so important physical concepts like the basic singularity properties of scattering amplitudes, or if I look at a singularity, what I should get is something that factorizes into lower point amplitudes at tree level. And at loop level, I should have a lower loop amplitude with two particles having equal and opposite momentum. Those are the two kinds of singularities that you can have that relate higher point amplitudes to lower point ones. So this basic equation, this we normally attribute to gluons going on shell here and here. But in the story of the amplituhedron, they have nothing. There's no space-time. There's no Hilbert space. There's just this object that lives in GK plus M with all these properties. But it reflects what the geometry of the amplituhedron looks like when you go to the boundaries. So when you go to the boundaries, you find geometrically that it splits. And it does exactly that picture tells you actually what the boundaries of the amplituhedron look like. Okay. So now, so let me already from here I can give a concrete example of the first thing that I wanted to tell you, that the scattering amplitudes are actually differential forms. So let's move from these toy examples to a first example of the simplest non-trivial amplitude, tree amplitude. The simplest non-trivial tree amplitude in this theory is the so-called next MHV amplitude, or in this language I'd write it k equals 1 for any n. And in the usual, I've been calling it A, I guess. In the usual presentation, there's a formula for it given by BCFW recursion relations, although it doesn't matter. I won't explain where this comes from, but I just want to write down some specific formula. So the object is given as a sum over a basic thing that depends on 5 twistors. Now, that basic object explicitly, that depends on 5 twistors, 1, 2, 3, 4, 5, depends on so that's what it is explicitly. So as promised, it's a function of these z's. The z's, I'm suppressing z's here, so these are all just the bosonic z's. I'm contracting them with epsilon symbols. And here's the dependence on the Grassmann variables, which are these etas. Okay, so there it is. It's a function of weight 4 in the etas, and that's a standard expression for the amplitude. So that's what the amplitude is in completely standard presentation. The amplituhedron asks you to think about this object entirely differently. So each one of these II plus 1 JJ plus 1s, first of all, before you even think about a form, those are simplices that live in a 4-dimensional space. And those simplices together are tiling and triangulating the amplituhedron, which in this case just happens to be a polytope that lives in this 4-dimensional space. So it's as if someone gave you the collection of triangles 1, 2, 3, 1, 3, 4, 1, 4, 5, and you notice that together they actually tile and triangulate a polygon, 1, 2, 3, 4, 5. Okay? So it's the analog of that in a higher dimensional space. So first, just geometrically, this is meaningful. This is triangulating something that's defined ab initio. I haven't told you the definition yet, but I'll tell you the definition in a moment. But the form that's associated with it, so each one of these guys is actually I promised you, from the amplituhedron point of view, each one of these things is actually a differential form that lives in y, and it looks a lot like what we saw for the form on the triangle. In fact, it is the generalization of a form on the triangle, except it's on a simplex in 2 higher dimensions. So there's a 1, 2, 3, 4, 5 to the 4th over now y, 1, 2, 3, 4, up to y, 5, 1, 2, 3. Okay, so this is, the top is the usual point of view, the bottom is the amplituhedron point of view. And indeed, you see that the z's are 5-dimensional vectors now. That's why I have to contract 5 of them together. And there's a y sitting here. So first, how do I go from this to reconstruct the ordinary amplitude? Well, that involves saying that y is just some vector. So I can always choose it to point in a particular direction. It's a 5-dimensional vector. I can choose it to point in that direction. That means that I can now take each one of the z's and divide it into a 4-dimensional z downstairs, and this xi that I mentioned down here. And in order to extract the superamplitude from the standard way we've been dealing with the amplituhedron, we then assume that this bottom component is actually infinitesimal. So we say that the xi, while being bosonic, is some fermionic phi dot a fermionic eta. And there's 4 of these guys and 4 of these guys. And so this expression is now a function of, is a polynomial in phi dot eta. And if we take this business part of the form, and if we integrate this over d4 phi multiplied by this thing, then we precisely get that thing. Okay? So that's the usual picture, that it's a form that lives in y space, but which we can interpret this way to become a function of ordinary momenta. Now, what's the new picture that I'm talking about? Well, you have to remember that I told you that this form has logarithmic singularities on the faces of the tetrahedron. So another way that I could write exactly this same form, so the same omega, this omega here, this omega I can also write as d log, just like I did for the triangle, d log y, let's say 1, 2, 3, 4, over y, 2, 3, 4, 5. It's 4 d logs to d log y 1, 2, 3, 5 over always y 2, 3, 4, 5 downstairs. I just choose one of them canonically and I divide by it. All right, so that's what this form is. And these d's, I emphasize, act on the y's in this picture. Okay, so let me be very explicit. The z's, the z's are completely fixed external data. Okay, and you can very easily check if you take all those dy's, you get exactly the expression that I wrote down here. But now comes the interesting twist. Because imagine that y is a vector, right? Is a point in this, y is a point in this 5-dimensional space, projected down projectively 4-dimensional, but it's really a 5-dimensional vector. Now imagine what things would look like if I just looked in the direction of y. So y is a point, I have a whole bunch of other points. If I look in the direction of y, so y gets projected down to the origin, I get a 1 lower dimensional picture, right? So that's just the standard notion of projection. I project through a point, that means that I look at all the other points modulo anything proportional to this point that I'm looking at. So if I project in that direction, I have a 3-dimensional picture. Four dimensions projectively going down to 3. So in that 3-dimensional picture, all of the, I would have 4-dimensional vectors left, and all the brackets between them in the projection are exactly the ones that I have here with the y put in. So I'm going to do something else. I'm going to write down exactly the same expression, d log, now 1, 2, 3, 4. So this is now over 2, 3, 4, 5. d log 1, 2, 3, 5 over 2, 3, 4, 5. Now, what could this mean? Now the z's that occur here are not these big z's. These big z's were 5-dimensional vectors. The z's that occur there are the little z's. They're the actual physical momentum twisters, okay? The very things that we started off life with. Literally those guys. So now I'm going to imagine that these d's act on the z's. They were acting on the y's in the amplituhedron picture, but in this picture, I'm going to imagine they're acting literally on the z's of the ordinary bosonic momentum twisters. I stress for the 5th time, this is not some extra fancy space. The whole structure is going to live in the space of kinematical external data. Bosonic kinematical external data, no super variables, ordinary bosonic kinematical external data. But where does the super stuff come from? If I take this differential form, the claim is that it is exactly delta 4, 1, 2, 3, 4, dz5 plus cyclic divided by 1, 2, 3, 4, up to 5, 1, 2, 3. In other words, it is literally the superamplitude, but where the Grassmann variable eta, you replace by the differential form dz. It's the absolute dumbest thing that you might think of doing to begin with. After all, when have we seen Grassmann odd variables before all the fancy business about supersymmetry? Differential forms are Grassmann odd variables. Okay, so it's the dumbest thing you could imagine doing is to just replace the super variables by the dz. That's a thought many of us have had for many years. Why have we not done it before? It's because it seems strange. Because we know that the z's are acted on by their own SL4 conformal symmetry. The etas have an SU4R symmetry, and there doesn't seem to be any reason to connect the two of them. Whereas if you make the eta equal to a dz, it appears that you are tying them to each other. And in fact, if you wrote down random differential forms, it would not work. But the differential forms that are attached to the amplituhedron in this way are guaranteed to always work. And in fact, this is a more direct way of establishing the connection between supersymmetry and the Grassmannian than has been established already from a number of other points of view before, but I think even more invariantly now. Okay? So you see it in this simple example that that if you take this differential form, it is the superamplitude. You can read out all the components just like you do from the ordinary superamplitude. But this general idea is going to extend. Okay? So the actual amplitude is a differential form on the space of external kinematical data. So now what I have to tell you in the remaining time that I have is what determines this differential form now. Now we're just in the space of ordinary bosonic data, nothing else. In that space, what is it that determines what that form is? What happened to this geometry of the amplituhedron, this region and so on, which I haven't described to you yet? And that's the binary code part of the story. Okay? So let me move on to that. And at the end, we'll do a little calculation because we can really do an ab initio calculation of, it's a very simple one, but all the one loop amplitudes in this theory we're just going to compute by keeping track of some plus signs and minus signs. Okay? So we'll get something concrete out of it in a moment. Okay, so now let me first tell you what the usual definition of the amplituhedron is. And I won't even give the whole one because we're going to give a different one. But just to give a sense, if we go back to a triangle, if I have the vertices of the triangle Z1, Z2, and Z3, if I want to think about all the points on the inside of the triangle, any points y on the inside of the triangle, one way of specifying it is by saying y is some C1, Z1 plus C2, Z2 plus C3, Z3, where these C's, so y is a vector, three-dimensional vector. This is a two-dimensional picture, but everything is done in projective geometry. So these are three-dimensional vectors up to rescaling. And so the points inside the triangle are of this form, C1, C2, C3. Of course, I can rescale them by any constant. So there's a GL1 that I can mod out by. but they all have to be positive. Okay, so all these CAs have got to be positive. And if they're all positive, then it's like a weighted sum of the points, and you're always on the inside of the triangle. Okay. Now we can extend that definition to the inside of a polygon. If the polygon is convex, so we have to demand that the polygon is convex. That's already an interesting restriction on the external data. It's a big open region in this set of external data. But for the polygon to be convex, we actually have to have that the z's are positive. All these determinants of ZA, ZB, ZC, if they're ordered, these all have to be positive. So this is in order for the polygon to be convex. But once it's convex, all the y's, again, we can write as C1, Z1 plus up to Cn, Zn in exactly the same way. So now the C1 through Cn are defined mod GL1, and all the C's have got to be positive again. Okay. So this is a very standard way of talking about the inside of a polygon. We can generalize it to the inside of any polytope. If you give me the vertices, I take the convex hull of all the points, and that defines the inside. So that's what it means for these coefficients to be positive. Now we can generalize this into the Grassmannian. We can say instead of having one y, we have k y's. So that gives me a k-plane in k plus m dimensions. And I can ask it that it's a linear combination of my external z's. So alpha runs from 1 to k. It's a k-plane. I runs from 1 to k plus m. The z's have got to be convex in the same sense. So that means that if I take any of these k plus m determinants of the z's when these indices are ordered, that these all have to be positive. And finally, the c's have got to be positive as well. But because there's a GLK symmetry acting on the y's that makes this a k-plane in k plus m dimensions, the positivity constraint on the c's has got to be compatible with that GLK symmetry. So it can only be a statement about the minors of this matrix, and it is indeed that the minors, CA1 up to CAK, all the minors of C have got to be positive when they're ordered. So just this little definition, this part, saying that we have K by n matrices, all of whose minors are positive, that's the definition of the positive Grassmannian. So we can define it in one line. But as you see, this is defining what the analog of the individual possible triangles are, the individual building blocks. The space itself, the amplituhedron itself, is the positive combination of positive external data. So this cuts out some region inside GK, K plus M, and that region is the tree amplituhedron. Okay. Now, already for the case of the polygon, we see that this definition, it's a perfectly fine definition, but it's very redundant. And it's actually not, computationally effective in the following sense, that if I hand you some y, I say here's a y, is it inside the polygon or not? This is not an easy way to check whether it's inside of the polygon or not. You've got to scan over all the possible ways that you could choose C's and see if it can be written in that form. And that's not easy to do. It's a perfectly correct definition, but it's not easy to do. Now, in the case of polygons, there's a number of other definitions that we have that are more effective. For example, these are standard classic things about polytopes. Another thing we could do is say, not that you're a positive combination of these points, but that you're on the same side of all of these lines. Okay? That's a way of defining the inside of a polygon by a bunch of inequalities, which you can certainly do. You can say that the polygon is defined by the set of inequalities y12 is positive, y23 is positive, up to yn1 is positive. Okay, so this is the face-centered way of talking about a polytope. You specify what the faces are by a bunch of inequalities and you cut out the space. The first definition is the vertex-centered way of talking about what a polytope is, which is the convex hull of all the vertices. And it's a very simple and classic theorem from the late 1800s that these two definitions, if one is true, the other is true, and vice versa. Okay? But this definition is quite effective. If someone hands you a y, you can check, is it indeed true? Is all these y12s, et cetera, positive? So we tried for a long time to try to generalize that, and there's lots of obstructions, lots and lots of obstructions to generalizing this directly. In fact, there is a story. If I had another hour, I would actually tell you a much more rational story, which makes what we're talking about next seem much more inevitable, where there's an intermediary between what I'm about to tell you now and this very simple thing that involves the observation that in the case of a polygon, you also have winding number 1 around a point on the inside. So there's a topological description as well, that if you have a point on the inside and you follow the boundary z1, z2, z3 up to zn, it winds around the origin once. Okay? So it turns out that there's a topological description of the amplitahedron, very beautiful topological description of it, purely topological description. But I'm going to skip over that to get to the most fundamental description of all, which is this binary one. And the root of all the problems and why it took us so long, and if you've suffered through any of my talks on this subject over the past many years, I always start with the stupid example of drawing points on the inside of a triangle. The difficulty is that that example is not simple enough. Okay? We did not actually start with the most primitive thing. As always, you always have to do the simplest things in the simplest, best possible way, and then things start making sense. And the difficulty is that we started with the damn triangle. In fact, we should start with an even simpler notion of being on the inside of something, which is an interval. Okay, so let's talk about what it means if you have 2 points, 1 and 2. What does it mean to be on the inside, to have a y that's on the inside of the interval versus having a y that's on the outside? What distinguishes these two things from each other? Okay? And here, of course, there are all the things. It's true that when it's on the inside, you can write it as a positive linear combination of 1 and 2 and so on. But there's a more primitive thing, which a child would know, who doesn't know how to add. Okay? The more primitive thing is if you're on the inside, if you walk from 1 to 2, you have to hit y in the middle. Okay? So what does that mean? That means that if you take the path from 1 to 2, you have to jump over y once. Okay? Whereas, so inside means that you jump over y once. Outside means that you jump over y 0 times. Okay? Now we can say this slightly more. We can say this slightly more invariantly. That this means that if I look at y1 and y2, that this sequence has to have one of them positive and the other one negative. Okay? Now, what if just for fun, I had 1, 2, 3, I had a whole bunch of guys, and there's n here, and 1, and y is somewhere in here. Then what would it mean that y is in the middle? It would mean that in this sequence somewhere, y1 up to yn, here it starts positive, here it starts negative, and somewhere it has to flip sign exactly once. Okay? So that means that this sequence, y1 through yn, has precisely one sign flip. Okay? So that's the most primitive notion of inside, is that for the usual situation if we have precisely one flip of sign. Okay, so now we're going to generalize to the amplitahedron, and remember I told you the amplitahedron is labeled by a k and an m, and I said in physics we need m equals 4, and actually we had seen indications that we need m equals 2 and other things. It's sort of funny that we needed different pieces for different pieces came up in different applications. But in fact, all of them are there, all of them are relevant, and the most fundamental and primitive object is the m equals 1 amplitahedron. Okay? So we can ask the question, when are you in the m equals 1 amplitahedron for general k? So m equals 1, so the external data is k plus 1 dimensional vectors, and we have a k plane, y. So we're going to ask what happens when I project through y. Okay, when I imagine projecting through y, I'm going to go down to a one-dimensional picture. In that one-dimensional picture, y is going to be an origin, and I have the rest of the z's sprinkled around it. And I can ask, what does that pattern look like? What does the pattern of all the rest of the z's look like? And the answer is that the pattern, to be inside the amplituhedron, you have to have, there's a new variable k, you have to have k sign flips. Okay? So that's it. That specifies being in the amplituhedron. Okay? And so I can just say it in this algebraic way, that if I take this sequence y1 through yn, it has exactly k sign flips. Okay? That's for the m equals 1 amplituhedron. Now what do you think the definition is for the m equals 2 amplituhedron? The definition for the m equals 2 amplituhedron is that if you now project the external data through any point to go down from m equals 2 to m equals 1, that any way that you do it should end up in the m equals 1 amplituhedron. So that means, for example, that to be in the m equals 2 amplituhedron, this sequence, I'm going to choose to project through the point 1. So y12, this sequence, y13 up to y1n, has k sign flips. For the m equals 4 amplituhedron, it's that y1, 2, 3, 4, y1, 2, 3, 5. I choose to project through 1, 2, and 3. I can tell you a few more rules about the way this projection is done, but it's completely canonical. This has to have k sign flips. Okay? So the y's that are inside the amplituhedron have the following property. If you project through y, let's say we have m equals 4 for ordinary amplitudes. If you project through y, you get a picture of the ordinary bosonic momentum twister external data. Okay, but there's something special about what that picture looks like if you got it from the story that I'm talking about projecting through y. Those bosonic momentum twisters don't look random. Okay? What they look like is the following. If you take that picture of the these ordinary four-dimensional vectors, and you project through them in this way. You look in the direction of 1, and then 2, and then 3. Or in fact, any a, and any b, and any b plus 1. And these ways of doing projections are canonical things that preserve the underlying positivity. Any such way of projecting, any way at all, the ultimate one-dimensional line picture that you get has precisely k sign flips. So that's it. That's the object. Okay? So that gives you, in the space of external kinematical data, there are those configurations that have this property that when you project through them, you have this binary code. You always get the same answer. No matter how you do it, no matter how you look at it, you always get k sign flips at the bottom. And then in that space, on that space, which as I mentioned before also has a topological characterization, but on that space, just in the space of ordinary external data, you have to find a differential form that puts logarithmic singularities on the boundaries of that space. That is the scattering form. Okay. So this is finally a definition of the scattering amplitude. There's no y's, there's no supersymmetry manifestly. It just lives in ordinary bosonic space of kinematical data, and it's completely, as you see, it's essentially completely combinatorial. These sign flips are the so I'll say one final thing before ending. So this was a story for trees. What is a story for loops? The story for loops is that in this space, in this momentum twister space, in addition to the external data, in addition to the z's, you have a bunch of lines. Those were the loop variables, right? So what has to happen? Now I have a line as well. I can do one more thing when I have a line. I can project through the line. So I can go from the three-dimensional picture of the external four-dimensional non-projective, three-dimensional projective picture of the external data. I can project through the line to go down to a two-dimensional picture, one-dimensional projective. Okay? And where do the lines have to be? The lines have got to have the properties such that if I project through them, I have k plus 2 sign flips. Okay? And the k plus 2 is actually forced on you. There's really nothing else it could be. I don't have time to explain it. But so the real space at loop level is now you have the z's, you have a bunch of lines, and you have to have the property if you project through the z's, you have k sign flips. If you project through any one of the lines, you have k plus 2 sign flips. That means that geometrically, the full amplitahedron is actually the intersection, the simple intersection of two spaces. It's a simple intersection of the m equals 2 amplitahedron for k plus 2 planes. And the k planes that live in the k plus 2 planes have got to live in the m equals 4 amplitahedron. So it's just the intersection of those two spaces with each other, with finally one last condition. And the last condition is that all these lines, if I have multiple loops, A, B, C, D, E, F, they all have to be mutually positive with respect to each other as well. So the A, B, C, Ds have got to be positive if I have more than one loop. So that's the geometry. The lines have got to be mutually positive. The external data has got to give you the binary code, and projecting through each one of the points has got to give you the binary code with 2 more flips. What's interesting about this, and I'll just end with this, unfortunately I didn't have time to do the little short computation for you, but we have to get to the boat. The organizers were very, very smart in arranging. Matthias is the only person who can shut me up in finite time. I mean, not even, but it's really, really impressive. I got to figure out how you do it. So, but let me just summarize. What's interesting about this story now? First, I don't have time to explain, but it's actually effective for doing calculations. So, what in the usual amplitahedron story involves thinking about triangulating the space. Very often boils down to just drawing patterns of plus, minus, plus, minus, plus, minus, all the possible ways, and each way corresponds to one piece of the amplitude. So, that's an enjoyable way of doing calculations in low loop cases. But more conceptually, what's interesting about it is that I think we're finally starting to see, from this positive geometry perspective, some of the very important physics which has been missing for a long time, at least hints of a connection to some of the important physics. And thinking about amplitudes, after all, we know physically there are many qualitatively different parts. For example, there's one part of the story that has to do with infrared divergences and the cusp anomalous dimension. And that famously connects to all the incredible work that has been done by integrability people over the last decade or so. Okay? So that's completely about the 4-particle amplitude. Okay? So part of the problem should be special about the 4-particle amplitude, right? And understanding that fully. Then there's trees, higher K, all the rest of that. That's somehow conceptually a totally different part. It doesn't seem directly connected to that one. And anyway, there are other aspects. In our previous understanding of the amplitahedron, which was more formal, less effective, all these distinctions were blurred. There was just one set of positive geometry and it all came out of it. And as I said, you could check locality and unitarity were outputs with some work you could check. In this picture, we really see all the different pieces, physical pieces, coming out as different parts of the mathematical problem as well. For example, I told you that when you're at multiple loops, part of the problem is to just figure out how to deal with the mutual positivity of all these different lines. That problem is essentially the 4-particle problem. Solving that problem, the mutual positivity of a whole bunch of lines, is essentially the 4-particle problem to all loop order. Okay? I didn't have time to explain it, but this topological picture, which involves keeping track of some winding numbers, 1 and 0, not just sign flip patterns, but winding numbers, actually is associated with the geometry not just for the amplitude, but for the correlator. The light-like ligament of the correlator is directly related to the geometry of the mutual positivity of all these lines. That's the 4-particle part of the problem. There is an essentially one-loop part of the problem, and there's a tree part of the problem, and all of those things are now seen as natural, different ingredients in this much more intrinsic picture of the amplitahedron is. So I hope if we make some progress, then it can actually connect. Really, I think the most pressing thing in this business is to try to make some direct connection with the cusp anomalous dimension story. I hope if you make some progress on that, you might invite me or one of my collaborators back in a number of years from now, and we'll give you a progress report on it again. Thanks a lot.
The whole problem seems based on the assumption that there's only logarithm similarities. Is there a reason?
No, in fact, it is extremely surprising that scattering amplitudes have logarithmic singularities. That's one of many. I mean, there are a number of things, but I'll just give you a very simple example. I won't take too long doing it, but even you do something as dumb and familiar as this. You look at one loop, this box, right? If you're a normal physicist, you would say this is D4L. Even if you think of the form, you'd say there's some L here, 1, 2, 3, 4. You'd say it's D4L over L squared, L plus P1 squared, L plus P1 plus P2 squared, L minus P4 squared. That's how you write it in all the books, right? It is not at all obvious that there's a choice of variables that turns this into dx over x, dy over y, dz over z, dw over w, but there is. This thing has logarithmic singularities, okay? Not at all obvious. The connection to the Grassmannian makes it obvious, and in fact, that's what brings all of this stuff out. So you can ask, are all amplitudes like that? And the answer is, in gauge theories, that's the most complicated singularity that you get, are logarithmic ones, okay? Then the challenge in going beyond n equals 4, so there's some universal things that have logarithmic singularities, which are there in n equals 4 as well as in QCD. The challenge in QCD is you have less singular things. You have things that have logarithmic singularities in just rational functions, or said another way, they have, for example, double poles or higher poles. So, but those are somehow simpler things. There's always choices of coordinates that trivialize them, whereas there's never choices of coordinates that trivialize logarithmic singularities. So all the physics of the renormalization group, ultraviolet divergences, all of that stuff that's there in QCD and not there in n equals 4 has to do with those, in a sense, simpler kinds of singularities. It's not at all obvious, but there's evidence up to 3 or maybe even 4 loops by now, I don't know, that in n equals 8 supergravity as well, you only have logarithmic singularities. That's much more surprising, but and it may well break down at some loop order. But I think part of the whole point is that people have looked at amplitudes or even integrands for decades. But the novelty here is to realize that these rational, naively rational functions, once you start thinking of them as forms, even at this primitive level, once you start thinking of them as forms, these rational functions are also telling you a geometric story by keeping track of where their singularities are and thinking about the hypersurfaces in momentum space or in space-time that correspond to those singularities. They're also telling a geometric story. So reading off geometries from singularities of these naively rational functions has led to progress in planar n equals 4 and will likely lead to interesting things for any field theory, I think. Yes.
I just wanted to know how where the expression arises. I mean, how they simplify. I don't need the projections.
Yeah, you see, here you saw that what determines the object is to project extremely. So you not only project through y, but once you get to the space of these bosonic data, you even project through the data to do anything you can to get to a one-dimensional line. Okay, but you can. And that's what turns it ultimately to this sign flip statement. But you could stop. You could stop just projecting through y, so you just have these bosonic z's. And then it turns out that being in the amplituhedron means that this pattern of z's has a specific winding number around y. Okay? If you have m equals 2, it's literally a winding number on a plane. For higher winding, it's an S3. It's an S3 notion of winding. Okay? So, but it's something you don't have to do it. It's a trivial. There's nothing hard to calculate. You just pick a ray out of the origin. You count how many boundaries you hit on the way out. Okay? So that's the notion of winding number, and having maximal winding means that you're in the amplituhedron. Having minimal winding means that you're, roughly speaking, in the parity conjugate of the amplituhedron. Yes. Oh, is that allowed? Yeah. Okay. Sorry. Yes.
So, An attractive feature of the Grassmannian is that it has Yankean symmetry
Yes.
of amplitudes built in.
Yes, yes.
How about Yankean symmetry in the amplituhedron? If I'm not mistaken, in the earlier formulation that was more obscure.
Yes, yes, yeah, I don't know. It's an excellent question. I think in this formulation, it should be, well, you see, in this formulation, this differential form is the superamplitude. So you can really go back and everything we said about the connection with the Grassmannian and Yangian invariance before goes through unscathed. It's just everywhere there's an eta, you replace it by a dz. What is, so that part is trivial. You could have always replaced an eta by a dz. What's interesting is the claim that the resulting object, this differential form, has a purpose in life directly in momentum twistor space. Let me say it another way. You could have always said, make eta dz, why not? Okay? But you'd all say, well, what do you gain? Just call it eta back. It's just some anti-commuting thing. The thing that you gain when you call an eta dz is that it makes you think about something that you don't think about if they're just etas. You think of integrating them over cycles. See, if they're just etas as variables, you don't think of using those d's to do integrals over cycles. Now you can, now that it's a form, it's very natural to think about doing integrals around cycles, and you discover logarithmic singularities, and you discover all the rest of the structure. In a sense, if someone hands you the amplitude, I could reverse the whole story. Someone hands you the amplitude. You have the fun idea to replace the etas by the dz's, and you say, oh, now I can integrate around cycles. And you say, oh my God, if I integrated, notice I always get these logarithmic singularities. Where do I get logarithmic singularities? When these sign patterns all work out right? You can read the entire story backwards. Okay? So I think it should make it easier to describe what the Yangian is, but it's still not 100% under control. I think it'd be very important to try to understand it better. Even more exciting to me, but we haven't seen anything, we haven't managed to make it concrete at all, would be if there was some completely bosonic notion of the Yangian in the original y variables in the amplituhedron. That would actually, I mean, independent of this story, that would make me very happy, but we haven't managed to find an effective one. Yeah.
Okay, so